So the next topic is about serial interfaces. There are several kind of serial interfaces. For example, there are some devices. I actually had some material somewhere. Sorry, I haven't included those here. I try to find them. But anyways, fundamentally there are different standard serial interfaces used with the microcontrollers. The most common ones are this traditional universal asynchronous receive transmit kind of the transmission. So it's 8 bits and usually it's a one line out and one line in. And then there are these the synchronized ones. Most common ones are I2C, SPI, and one wire. Yes, one wire. That's also synchronized communication. Although there's the difference between synchronized and async, the signal is basically that on synchronized there's also a clock signal. One wire does not have clock, but it's still considered synchronized, I think. Okay, but anyways, it looks like it wouldn't be, but but anyways, so this normal UART, normal old-fashioned UART kind of the transmission, which was first used, for example, on mainframe computers and to hook up the terminals to the line. Maybe I should write something on the table. Okay, something. There we go. I'll turn off that for a while. So about this what kind of the serial the transmission. Basically, this is a device that can be used for example, RS-232 communication line. But this is actually a standard, which defines also the voltage lines and that kind of stuff. And this standard was defined for hooking terminals to a computer or mainframe. And basically hook up a terminal or mainframe to modem, and that would go to the telephone line and hooked into the other computer on another terminal. So ask your grandfather what this modem looks like. On the other hand, if you are subscribing any data subscription like DSLs, that's actually a modem right there. So it just translates this serial line data so that it actually travels well on those telephone lines. Anyways, that one is a simple protocol which has some parameters like speed or bit rate. Yeah, not speed, but bit rate. And only specific bit rates are available or can be used. Most common are 9,600 and 19,200 bits per second. But there are also, 2400 and such kind of things. There are several ones, but these are basically coming from the history. I was really happy when we, on university where I was studying, we had first the bit rate and 150 bits per second between terminal and the mainframe. And then they doubled it to 300. Then you could actually type so that you can see what, all the characters. You need to wait. Okay, so bit rate, then number of bits. Number of bits. Okay, number. Number of bits. Usually, it can be also smaller than that. 8 or 7, depending, but that's most common. Down to 4, actually. Less than 4, it's not allowed. Then parity. No parity is the most common, even parity or odd parity. Nowadays, usually the data integrity is tested by some better means than just one single bit. For example, cyclic redundancy checks, CRC numbers. And the fourth one here is actually the number of stop bits, either 1 or 1.5. And this actually, how to make 1.5 bits? Well, this is actually the just a pause. How long pause you can have to have in between two the transmissions. But, one is just enough most of the time. Okay, so that's the RS-232. Or without that buffering, there is a UART inside, which has the line buffering for output and input. Okay. Anyways, that UART has 2 channels. One is for transmitting and one is for receiving. And if you have any other similar DTE, data terminal equipment, another DTE equipment here, it also have the TX and RX. So, well, you just need to cross the lines, which you will need to do on our today's exercise. This one here actually is the PSOC 5 development board, but it also is a but it also has the serial to USB device inside of it. So you can use this one for debugging even with lower voltages than 5 volts. So you can run 3 volt system and use this one for transmission between computer and your device. So in this device, basically, you have those pins 12.6 and 12.7, which are marked on the other side. What you need to hook up between those, and common ground. GND. And then you have a data transmission lines ready. You just need to fix the communication parameters, bit rate, bits parity so that they match. Okay. How do you know the parameters here? Since this is, it's kind of debugging device. Well, when you plug that one into PC, then you go into PC and take the, let's see, it's the device manager. You can actually then see the ports, and on ports you will find COM port. It looks like a virtual serial port there. If you have a ancient computer with real real RS-232, then that the development board actually has also that one. But not anymore. Not in laptops anymore. Not even in my laptop. Okay, so yeah, it's really ancient technology. Yeah. So basically, when you plug this one in, it will show up as a COM port and make a note of which COM port. Since you can then take the, say, some terminal program. In Metropolia, we are using TTY terminals, a standard terminal, and then basically there on this one you see the parameters, which you then put on your terminal, and then you can actually use your terminal program to communicate with your device. And okay, these parameters, of course, these must match your PSOC program. Okay, a bit complicated, but that's how you get it, the serial line run. Another serial line what we have today is the, was it one wire? Let me take a quick look at the, yes, DS18B22, or actually we had DS1820 devices to as a one wire temperature sensors. Take a closer look, since this looks quite the same as the device I gave you earlier. It's the same package. So make some notes on which one is which. Or, well, you have young eyes, so you can always, just read them. Personally, I will use this one as a magnifier. Okay, so there we have the one wire. It's a, was it Philips or some? No, it's not Philips. Was it on Dallas has the? Yeah, Dallas has the IPRs for the for the one wire. But the name one wire actually comes from the fact that it uses two wires. Okay, here we have the master device, which is powered normally. Then it has actually this one wire line going to the device. The one wire means that you can actually power it up also from this line directly. You do not need necessarily to power this one from any external power supply. But since that is available, why not to use it? Okay, in addition to that, I think you also need a pull-up resistor here. But anyways, the device here is designed so that actually it has also system to take some of the power to the small capacitor inside of the device. So the device functions without any external power too. And that another wire is this ground connection. But well, signal is in one wire. Good. It has its own protocol, which is not straightforward. And basically you need to read the that data sheet quite carefully, since you need to actually initialize it and set the internal register so you can read the data. But on that data sheet, there are instructions how to do it. I have the data sheet for that 18 plus 22, or 18B 22 plus, which is code compatible. But since we have that 1820, I would recommend finding the data sheet for that one. There is not much difference, but the 22 is a little bit enhanced version. Okay, so one wire sensor. So today, basically, you will start from the this earlier exercise. We had this sampler on sampling rate of 2 samples per second, and make that sampler actually also to sample the this one wire sensor. So you will go when earlier you just calculated the temperature from the analog sensor. Now you also go and read the value from this digital one wire sensor. And then basically earlier you would put the output only to LCD. Now you would be sending the data also to the serial port. Okay. You also need to, well, that will be the first part. Try to just add the one wire sensor in addition to this analog sensor and plot both of those here. Then modify so that you can actually have the serial port output. And when you have those, then you can actually finish the exercise by doing it a kind of intelligent sampling circuit. So it also reads. Basically, your system would wait for the command. So there's the last one on the task. They modify the code such that the system waits for a command from PC and does the following. Well, so basically you type here A, your device should reply by a identification string. Simple. And that should show up on your terminal. Okay? And S means that it returns one sampler from ADC, actually ADC and one wire. Okay, I need to modify that a little. Where's my exercise 4? Now, analog and temperature sensor. There, single value. And then C means sample and return data continuously, and X is stop sampling. Simple kind of the interface. So after that, you have a data logger. Haha. A lot of wires. It looks like a mess, but anyways. So that's the stuff for today's exercise. Today we won't have much of challenge yet on fitting all of that stuff inside of the piece, but tomorrow we will have. Where's my? Okay, there it is. There we go. So that's the wait a minute. That's today's exercise. So we have one wire sensor and the analog sensor, and then basically send that one to LCD and USB serial port. Let me change that a little bit. So. So that analog sensor we already have. We just add there one wire sensor. Should I actually change that one a little bit? So that we have LCD part we have. There. Better. So analog sensor LCD we have and the sampler inside. So basically what we could do now is to just to clone the project, but it's not 2B, it's actually I think it's 3, exercise 3. You know, it's too easy to leave those error sheets since I can change them as I speak. Okay. Anyhow, let's take a quick look on, or a better look, what we should be doing today. So this is the exercise 3 project. First thing first, so make sure first that it works. So sample two samples per second, and give us values that are something above 25. Since my sensor gives 27, you have something like 26. Yeah. Okay, and that's my code. C. Process, display, and COM. That COM is already there, so I encapsulated those in on different files. Yes. So basically, how to encapsulate the code, I created 2 files. So one is process.h, where I put the code, and also then the process.c, which basically is just the prototypes for the functions. So process.h is simply these 3 prototypes, and that's it. And process.c has those functions: process, display, and then communicate. So that's one way of doing stuff. Yes, exactly. So if I have on main.c, I have this, let's see, main.c. Main.c, I have these the global variables. I use only these 2 global variables on my process. since I don't need the times up, since I go there only when time's up. Okay, and on process, to read those correctly, you declare those as external without the initial value. Otherwise, that's a syntax error. Okay, so that's the real variable, and this is just telling to the linker where the variable is found. So it's externally. It's not inside of this scope of this file only. Okay. So chip level. We need yes, exactly. I was about to do it, but all right, new project. PSOC exercise 4. Actually, I already have one of those, so I'll just put version B. I tried it first. Clone existing and exercise 3, and that CMX file is the project description file. And then we'll wait, and it blinks, and now it's exactly the same. It's a good idea to actually build it. Build it and program to make sure that nothing changed during our cloning process. For example, you could have accidentally clicked the different processor there. Or not that accidentally. If you find out that, okay, this device does not have enough of resources, you could go to a bigger device. Okay, so I have this 16-bit timer and that one, and it seems that it still works. And I have all those code also here. That's nice. Okay, and those are local copies, and more then I could actually start adding some devices here, and I need UART and yeah, one wire. Yes, I'll show you what happens. There's small hiccup, not a problem, but a hiccup here. So if I add here the UART, the UART can actually be let's see, placed to, well, it seems that it can be placed only to this location, right? No, it actually can. Oh, no. Yeah, that's the only place we can put it. And if I try to add here the one wire module, it cannot place it anymore. So that's the hiccup. So for that reason, actually, what I can do, I could actually move this block down here. I hope, oops, not there, there. No, it doesn't move there. Okay, now there's a bigger hiccup. We have to go to 8-bit timer to make room for one wire module. No, it doesn't go there. Does it go? Oh, yes, it did. Excellent. Yeah. So otherwise, I should have got, you know, a make this timer to 8-bit timer. Yeah. Yeah. And now, if we are lucky, one wire goes there. Yes. And we have used all the resources what we have. All the digital resources are there. Done. Okay. If you want some more, you need to actually get rid of the one 8-bit timer there. So you would make a 8-bit timer instead of a 16-bit timer, and then have a software timer inside of that 8-bit timer interrupt service routine. Yes. But now we are still lucky. We can put the UART there and one wire block, and then we still can run the timer. Yes, but only for transmission. The receive actually requires this hardware block. Tomorrow we will add here SPI master, which means that we must go and break the timer. We have to break the timer. Haha. Or get some bigger chips. Do we have actually bigger chips? Not in here. Maybe Umansky has, but not tomorrow. Oop. Well, that's SOC 5, which has different tool set. Yeah. Well, it doesn't have that much limits. It has less hardware blocks, but it's ARM processor, so it has lots of processing power there. Okay. Anyhow, now I have the UART and one wire block, and then basically what I need to do is now is a good time to check the bit rate for this one. Do I have enough of ports? Oh yeah, I can actually get rid of. That I would need for a while. This would be better port. Okay, I'll just change it. So when you plug this one in, it installs the drivers, but these are legacy drivers, and legacy drivers, it shows the device. Device setup goes installing, and it says installed something there. Then I can go to the device manager. Wait a minute, where's my device manager? Device manager. It's on your control panel. There. So device manager, and under device manager, the ports, it's supposed to actually show up here. It does not. What's that? It should be actually a COM port. Maybe. Okay. Now it's installing. It's installing, but it's installing. Okay, close that one. Okay, no. Yeah. Anywhere on your computer, USB. Yep. Yep. So it basically installs the drivers, and so did you get the USB? Yes, and that you have port 4. Yeah, COM4. Good. Ah, yeah, Kitback bootloaders and such kind of. Yeah, okay, I have COM6 now. Good. So make a note on that COM port. And actually, if you use the same device but on another port, a USB port, it renumerates it. So next time you start the same thing, make sure that you have the same physical USB port. Otherwise, it gives it a different number. All right. So actually, now you can start communicating with the putty, for example. But okay, wait a minute. I was going to also check the settings there. All right. So actually, the port has setting for 9600 bits per second, 8 data bits, parity none. Okay. So bitrate 9600, 8 bits, no parity. Stop bits 1, but that doesn't really matter. All right. So if I now open putty, wow, you're running out of space on this PC. Oh, great. What? What is filling it? No, well, I'll do it later. This computer will be replaced at some point in any case. So I have been cleaning it for 2 weeks now. It's an old computer. Uh, yeah, I can. Yes, I can, but I will do it later. It shouldn't have any photos of it. Video. I'm streaming and saving. I probably should then get rid of the old videos. Yes, they are pretty. Yeah. uh, delete. Then go to the recycle bin. Where is it? Why it doesn't do anything? No, doesn't do anything. Delete. Yeah, that should be enough. Actually, that was Monday was very big file. All right, and then where's the where's the oh, that should be enough. So basically now it starts reusing those recycling bin. Maybe. Yep. Nah, who cares? I don't care. Oh, but anyway, so hopefully this will the system works. I need to do some housekeeping today, I think. Okay, sorry about that. So anyhow, so we have UART, we have the one wire block. Okay, UART has receive and transmit. Okay, now you just need to make sure that those pins are on correct pins. So routing the this transmitter output to which pin? The transmitter output will be, yeah, TX 1.2, port 1.2. Why am I using the same pins as on the other exercise? That is very strange. I usually don't. Do I get into trouble if I change this one to 1.4? Since I don't want to change this setup. I will change that port pin. Sorry about that. Okay, so port 1.4 as TX. Then I can have exactly the same, all the this servos and such kind of things there. I'm lazy. Good. So 1.4. Yes. Yep. Yeah. Oh, there is a recycling bin. I found it. Empty recycling bin. Yes. Yeah. Oh, okay. It has something like 10 gigabytes. Okay. Yeah. Alrighty then. So where I was. Okay. What transmit output should be on port 1.4. Okay. So we can connect 1.4 to row output 1 0. So not transmission clock, but the transmission out. So row 1 output, or row output 1 0 line can be connected then to odd 4. That will be even 4. That's odd 4. Yes. And this line can be connected to 1.4. Right. Then the input was on 1. Let's see. Okay, 1.3 was the receive pin, so the UART receive should be on. Okay, row input, that will be input 3, right? Yeah, but wait a minute. The interconnect first, so that interconnect is on. That one shall be connected to the odd ports, odd port line 3. Okay, there, and this one is then connected to port 1.3. Okay. Yeah. Okay, 1.3 and 1.4 are now for receive and transmit. The rest of the parameters, I leave you to it. Most important, how to actually get the correct bit rate. You can now, we haven't been using this far the VC1 and VC2 on this exercise. So basically, by using VC1 and VC3, you can get that clock rate very close to that one. It's actually at the quite on the early beginning of the of that data sheet of WART, how to get that bit rate, the dividers and such kind of things. Okay, so now we have receive and transmit there. Okay, the receive part also have the interrupt service routine. So again, you can make a hookup so that whenever there is a character coming, then it gives interrupt and you read what is the command. Okay. So what receive transmit? And transmit is very simple. You just give a transmit command. There's also a buffer that you can, software buffer that you can send strings using this WART. That helps a lot of the protocol. Otherwise, if we had just WART circuit and code, then you should do the basically the WART works such that you send one character by character, and you have to wait until the previous is gone before you can write your new one, unless there is a first in first out buffer. But this has the first in first out as software buffer. Okay, then the one wire. One trick about the one wire. Okay, one wire actually also uses this, one wire itself has only this one communication wire, but the only way you can connect PSOC is that you would have those blocks actually have either input or output. So basically you need to have for one wire, it has this receive and transmit separately. You need to also put the lines to the receive and transmit part of this module separately. And this this connection must be done externally. So for the bus, it's just one wire, but for this PSOC, it has two connections. And let's see. One wire, yes, port 1.7 and 1.6 are the output and input data lines. So one wire output is 1.7. Let's see, that's which one is the receive block and which is, oh, that's the transmit, okay. Transmit row, that's 7 should go there, and input for that receive goes to input 2 there. Yeah, something like that. And then, of course, the rest of the wiring. Okay. And rest of the parameters. Read the instructions how to actually set up the clock for the for this device. I hope that we don't need separate clock here. It must be 3 megahertz. Okay, you need to get this one from somewhere. 3 megahertz clock. Yeah, 24 divided by 8. Then you are also fixing the VC1. You cannot use it anymore to anywhere else. 8 and clock VC1. Okay. So as you can see, we are actually now fixing some of these global resources and kind of getting the point that we are closer to the performance limit of this device. But, you know, that's life. So, good. So one wire is there. What is there? You just need to, do the rest of these connections, and then basically on the main you will start modules, enable interrupts. The first thing what you should do is to test that you get some results on the one wire. Mm-hmm. Yeah. Yes. 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 You must change a lot of things when you change one thing on the timers or those system clock dividers. Yeah. Good. So, yeah, some coding. You need to do some coding here too. But I will let you to do it. I'm not showing you all the answers, just the problems and just the things that are hard to find. Okay, any questions for this exercise? UART, read the manual, data sheet, and basically, I think there was a somewhere there was a table showing, or was it table? No, it wasn't. Ah, there, clock. Ha, 9,600 bits per second. Okay, VC1 divider 8. That's good. It's basically the same as we already have there. VC3 divider 39. Make the source for VC3, the VC1 as a source for the VC3. Yeah, we got lucky. Good. Any other questions? No. Okay, then start working.